dynamics is the study of forces and how forces affect motion. When we do kinematics at the start, when we do equations of motion, we just look at how speeds change and how displacements and stuff like that change, without thinking about the forces that are involved. Dynamics is looking at that motion again, but now considering the forces that are involved. So my advice to you would be that every time you encounter a problem where there are forces involved, more than one force, generally there will be 3 or 4, is to draw a force diagram. So if you've got something acting along a horizontal surface, you can jot in what its mass is in here, and then you can jot down what the force is in the forwards direction, what the force is in the backwards direction, so this can be a certain number of newtons, and this will be a certain number of newtons. You can also jot down in which direction the unbalanced force is, because that becomes important, especially if you're looking at Newton's second law, more on that in a minute. So your unbalanced force could be in the forwards direction because it's going that way, and that also means that you've got an acceleration in this forwards direction as well. You can do something similar with something that's in the air. Something that's in the air will have a certain mass. You can again draw on that what the forces are acting here, so this will most probably be weight of a certain number of newtons. This will be some kind of thrust of a certain number of newtons that's sending it in upwards direction. It could be up thrust, it could be thrust from engines or anything like that. Again, you can jot down on here in which direction the unbalanced force is, and then you can also jot down in which direction the acceleration is. So just by doing a simple diagram, whether it's for vertical motion or for horizontal motion, you can figure out a lot more about how this object is going to move. Because already, if you figure out that the unbalanced force is in a particular direction, then you know that the acceleration is in that particular direction. If you find that weight is equal to this force in the upwards direction, then you know that the forces acting upon that are balanced. So it's at this stage that you really figure out which of Newton's laws you're going to use. I'll just denote them as N1, N2 and N3. So N1 is balanced forces. So anytime you've got balanced forces, you're going to cause an object to move at constant speed or to stay exactly where it is, to stay stationary. So if you draw out your force diagram and you end up with balanced forces, then you know it's going to be doing one of those two things. It's going to be moving at a constant speed, or it's going to be sitting still, it's going to be stationary. Newton 2 is basically F equals ma. So your unbalanced force is equal to mass times acceleration. So that just basically tells you that if you've got an unbalanced force going in a particular direction, like I've drawn in here, then you will have an acceleration in that direction. But the size of that acceleration depends upon the mass. The bigger something is, the harder it's going to be to accelerate. Newton 3, the less used of the three laws there, is action and reaction forces. So for every action, there's an equal and opposite reaction force. Doesn't tend to come up as much as the other two here, but it's still something that we need to know a little bit about. So that's how I would approach any sort of force problem, is to draw down a force diagram, indicate as much as you can on that, and that will help you to decide which of these Newton's laws you use, and it makes the problem much easier to solve. However, it's not just a case of having forces in straight up and straight down, or to the left and to the right. You can often have forces that act at an angle, and that tends to be where people get a wee bit confused. So the first situation that I'm going to go through with you is forces at an angle. The forces at an angle we treat in a similar way to the way that we treat the motion of a projectile. You have horizontal motion and you have vertical parts of the motion. You have the same with forces at an angle. You have force in a vertical direction and force in a horizontal direction. If you think about, if you picture carrying or pulling a box along a surface. I know it's not something that you do very often, but say you were pulling something along a surface, if you give this enough force, say in the upwards direction, then it's going to lift up off the ground. If you give this enough force in the horizontal direction, then you're going to cause it to move this particular way. If you give it a force at an angle, then you're going to have a mixture of force in the horizontal direction and in the vertical direction. And we can figure that out using components. So if we imagine that this is a triangle, like so, then we can figure out something for this which will give us the force in the horizontal direction, and we can figure out something for this which will give us force in the vertical direction. And if we call this hypotenuse here, we call this F. That's the force that is applied. So we've got 4 newtons being applied at 26 degrees. If we want to figure out what the force in the horizontal direction is, then it's F cos theta. Back in projectiles, we think about it as cos across. However, these forces can often be moved round. This can be rotated round, as you'll see in one of my later examples. So it's not always going to work that in the horizontal direction it's cos. If in doubt, think about it in terms of trigonometry. If we take cos theta, cos of this angle in here, say this is theta, that's going to be adjacent side over hypotenuse. The adjacent side is FH, the hypotenuse is F. If you rearrange that, then you're going to get FH equals F cos theta. And you can do something similar for this side here. FV, the force in the vertical direction, will be F sine theta. And the F sine theta comes from it's opposite over hypotenuse, so it's FV over F, and we just arrange it in a similar way, rearrange it in a similar way to up here to give us F sine theta. So if you want to know how much force there is in the horizontal direction here, then it would be 4 cos 26. If you want to know how much is in the vertical direction, then it will be 4 sine 26. You can see visually that there's going to be more force in this horizontal direction than there will be in the vertical direction, but that's where these come from, and we need to be able to apply these to forces acting at an angle. So let's look at a question for forces at an angle. So a box of mass 18 kilograms is at rest on a horizontal frictionless surface. Often you'll find that it is a frictionless surface because it's more complicated to include friction. A force of 4 newtons is applied to the box at an angle of 26 degrees to the horizontal. So this is the same diagram I showed you a wee minute ago. We showed that this would be our horizontal force and it would be equal to F cos theta. So we can carry out that calculation now. For part 1, the horizontal force will be F cos theta. So it's going to be 4 cos 26 degrees, which will give us 3.6 newtons. So that means we've got 3.6 newtons going in this forwards direction here. Calculate the acceleration of the box along the horizontal surface. Anytime acceleration is mentioned, we've already got an unbalanced force in this forwards direction. It is the 3.6 newtons because we don't have any frictional force acting this way. If you did, you would draw that in a force diagram and then figure out what the difference was and then use that in your F equals ma equation. So unbalanced force equals mass times acceleration. Our unbalanced force is 3.6. The mass is given up here as 18 kilograms. And then we solve for A, and we find it's 0.2 meters per second squared. The most common mistake that people make there is putting in your unbalanced force of 4 newtons here. Just as with projectiles, where you're given a speed at an angle, if you're given a force at an angle, you never actually use that value on its own as a value for force or as a value for velocity. You always use, you look at either horizontal or vertical on their own, because this is a mixture of the two components, horizontal and vertical. So if you're using a horizontal force, you need to think about horizontal values. Part 3. Calculate the horizontal distance travelled by the box in a time of 7 seconds. We've got all sorts of information about the motion, so anytime we do have information about motion, we write down SUVAT and we figure out which equation of motion to use. So although this is essentially a dynamics problem, you'll often find that you throw in a wee bit of kinematics in there, because once you understand a little bit about the force, it's relevant to mention something about the speed and the displacements of the objects. So we're looking for horizontal distance, we don't know what that is. U, it starts from rest, it's mentioned at the start there, so this is 0 meters per second. V, we're not sure of, we don't have a value for V. We do have a value for A, it's 0.2 meters per second, and we're given a time of 7 seconds here. So we're looking for S, and we've got U, A and T. It's not hard to see that it's S equals UT plus a half AT squared. So this will be 0 plus a half multiplied by 0.2 multiplied by 7 squared will give us a displacement of 4.9 meters. Now your classic sort of last question for 2 marks here, where something has changed, one thing has changed and everything else is kept the same. We've been through, kind of how to answer these. You can often answer them, with an equation, but I tend to use arrows in some way and then think about how that affects, your overall answer. So it's placed at rest again. That's the same. The force of 4 newtons again, but an angle of less than 26. The force is applied for a time of 7 seconds as before. How does the distance travelled by the box compare with your answer to A part 3? So this answer of 4.9, and you must give a justification for your answer. You could calculate it out. You could put a value in up here of less than 26 and then work it through. That's going to take you a wee bit of time though. What you can do is think about it. If you've got less of an angle here, then it's actually going to increase your horizontal force. So you get a larger value of horizontal force. It's not hard to see why that is, because this is a shallower angle, so it's going to have more force in this direction than it does in this direction. So your horizontal force is greater. You'd find that as well if you put in a smaller value here. Some people get confused because you put a smaller value and you think you get a smaller value out, but it's cos, it always goes the opposite way. If it were sine, that would be the case, but it's cos, so it goes in the opposite direction. So then think about the next step. If you've got less of an unbalanced force, then what's that going to do to the acceleration? So a greater unbalanced force, then you're going to have a greater acceleration. If you have a greater acceleration, then it's going to be travelling faster, the speed will be greater, so therefore the distance, S, the distance will be greater. So that's your 4 half marks there, and this is what you would describe in words. Remember, you're not going to get any marks for this little section, but you would use that to help you construct a word answer. So greater horizontal force means that there's a larger unbalanced force in the horizontal direction, which gives a larger acceleration. A larger acceleration means that it goes faster, so therefore it will be a larger displacement. Okay, this is forces acting on more than one object, and a couple of people have mentioned that this type of question, so I thought I would go through it because it always is something that is answered quite badly. This is from the multiple choice section, but there's nothing to say that you won't find that in a full written question as well. So you've got a couple of objects here. You could draw out a force diagram to indicate what's going on there. So these are joined together. We can write in the masses. So this is 700 kilograms and this is 1,200. They're joined by a coupling, that's got some sort of tension in it, and that's what you're ultimately looking to calculate. Tension, remember, acts towards where it's secured, so it's acting that way. You're given a wee bit of information about it. You know that the unbalanced force is in the forwards direction because it's travelling this way. So your unbalanced force you can indicate going this way. Therefore, that means that there's also an acceleration in that direction. And that gives you just about everything that you need for the next step. So assuming that the frictional forces are negligible, we're assuming that there's no other force in this direction. The tension in the coupling between the car and the horse box is. So you're looking for the tension in the coupling. The first thing I would do is calculate out what the unbalanced force acting here is. So F equals MA. Both of those things are joined together, so they're effectively acting like an object that is combined. So you can add your masses together. So you end up with 1,900 kilograms multiplied by an acceleration. The acceleration is given here as 2 meters per second. So that will give you 3,800. 3,800 newtons is your unbalanced force in the forwards direction. That's the force that's causing those two objects to accelerate. That unbalanced force is going to be what you use to ultimately figure out what this tension is. The next thing you need to do is to figure out what force this object is creating. You know, what unbalanced force is acting on that particular object on its own. So we do F equals MA again. It's accelerating at at 2 meters per second squared. Even though it's attached to this, you know, this is accelerating 2 meters per second squared, and so is this. So if we just look at the mass of that on its own, and we multiply that by 2, then we get 2,400 newtons. So there's 2,400 newtons acting on this alone. This overall force up here is 3,800. The force acting on both the objects is 3,800. If we break it down into the two, or the forces that are acting on the two objects, then we've got 2,400 newtons acting there. So it's not difficult to see that in order to get 3,800 going in this direction, we've got to add the tension to this. So your unbalanced force will be 2,400 plus whatever your value of tension is. This unbalanced force is 3,800. So your tension will basically be 3,800 minus 2,400, which will give you 1,400 newtons. So now we've got 1,400 newtons acting here as a result of the tension, 2,400 newtons that this object on its own is creating, and both of those add up to your unbalanced force of 3,800. So in any of those situations, first of all, calculate what the unbalanced force acting on both objects is. Secondly, figure out the unbalanced force acting on just one of the objects. And then thirdly, whatever force is left over, that will be your tension between the objects. Quite a complicated one, and one that people will stumble upon. It is tricky. Okay, next situation is forces acting down a slope, or it could be, you know, up a slope as well. So forces acting on a slope. If we think about what forces are acting there, then you know it's always going to have something to do with weight. You know, you set something off on its way down a slope, it's going to travel down that slope. We ask ourselves the question, you know, why does it do that? It does it because of gravity, but it's not just simply weight, which is equal to mg. It's not just simply weight anymore. Because we're at an angle, we end up with a component of weight. Because it doesn't just depend upon what the weight of this object is, how it will move, it also depends upon the angle at which the slope is sitting at. And the component of weight is equal to mg sine theta. And we can draw force diagrams for objects on this slope, and we can indicate the forces acting down the way and the forces acting up the way in the same way as we would for any other dynamics problem. But you need to remember this equation. You need to remember mg sine theta. You won't be given that in your formula booklet. So let's look at a question on something like this. So it's the same picture again as I've used. Slopes at an angle of 22 degrees to the horizontal. Each raft has a mass of 8 kilograms. The length of the slope is 50 meters. The child of mass 52 kilograms sits in the raft, and the force of friction between the raft and the slope remains constant at 180 newtons. So you could draw yourself a wee force diagram to indicate that you've got your component of weight here, and you've got friction acting up here of 180 newtons. The mass is 52 kilograms, and this is at an angle of 22 degrees. That just helps you picture in your head what's going on for the next part. So part A, calculate the component of weight in newtons of the child and raft down the slope. So it's mg sine theta, just like we discussed a wee second ago. So it's 52 times 9.8 multiplied by sine of 22 degrees. If you've got all that scribbled down in a diagram, you can just look at your diagram and pull that straight out. That will give you 220 newtons. B, show by calculation that the acceleration of the child in the raft down the slope is 0.67 meters per second squared. In the last wee question that I did, we didn't have to think about friction. The last two questions, in fact, we didn't have to think about friction because it was negligible. Here, there is a force of friction, so that's therefore going to affect your unbalanced force in the forward direction, so that's going to affect your acceleration. So the first thing you need to do is to calculate out what your unbalanced force is. So we've just calculated that the component of weight is equal to 220 newtons. So if your unbalanced force is in this direction and your acceleration is in this direction, your unbalanced force must be this minus this, which gives you 40 newtons. So we've got 40 newtons there. We can then put that into F equals ma. So 40 is this mass of 52 multiplied by A. So A comes out at 0.67. Oh, sorry. Yep, I've missed that out. We've got 8 kilograms in there, so this is actually 60. So 60 A, which gives you 0.67 meters per second. Sorry, I forgot about that. So 0.67 is your acceleration there, that's proved. Calculate the speed of the child and raft at the bottom of the slope. Again, as with the previous question that I showed you, it's equations of motion. Write down SUVAT and solve for whatever is missing. I think it's v squared equals u squared plus 2es that you use there, but I'm not wanting to go through too much of equations of motion. We'll just skip on to this second part here. A second child of smaller mass is released from rest in an identical raft at the same starting point. The force of friction is the same as before. How does the speed of this child and raft at the bottom of the slope compare with the answer to part C? So this is the same as that question a couple of questions ago. One thing has changed and everything else is kept the same, and you're asked to figure out what the change will result in. So you've got a smaller mass. It basically means that your component of weight, if you look at it, mg sine theta, if you reduce this mass, say down to 52, like I incorrectly put it in as, 52 plus 8, your component of weight is going to be less. So if component of weight is less, you look at how that affects unbalanced force. If friction is the same as before, then it means that your unbalanced force will be less. If unbalanced force is less, then it's going to affect the acceleration. So the acceleration goes down. So if acceleration goes down, something speeds up less quickly, then it means that your speed at the bottom of the slope goes down. So again, 4 quantities, 4 arrows, half mark each if you can transfer that into a written answer. And last one of all, and this does come up from time to time, and that's more than one force acting at an angle, which can confuse people. Again, I won't do all of the next question because we're looking to focus on the dynamics part here. So we can draw out a wee force diagram. We can indicate that this has a certain mass, and we've got, as is explained in the question in a minute, we've got a certain force acting on these wires, but that is a force that is at an angle, and an angle in this case of 21 degrees. So we've got to look at components of force again, and the main mistake that people will make here is thinking that that is your force in the vertical direction and is therefore F sine theta, but that is actually our classic sort of triangle turned on its side. So this is F, that component there is actually cos, which you could figure out, if you just scribble down that this is FH and this is FV, or whatever you want to call it, you can figure out through trigonometry that your vertical force here is actually F cos theta. So you've got a force acting there, but you've also got a force acting here. So your total force in the upwards direction, if that's what you're looking for, which you will be in a minute, is going to be 2 times FV. So it's going to be 2 times this to give you your force in the horizontal direction. The vertical direction now. So that's what you go on to do in the first part there. Calculate the vertical component of the force exerted by each chord just before the capsule is released. So for that you're going to use F cos theta, because it's each chord, so it would be, the tension is given here as 4.5 times 10 to the power 3, so it would be 4.5 times 10 to the power 3 cos 21 degrees, and then that'll give you an answer. Calculate the acceleration of the capsule. You need to know again what the unbalanced force is. In this case you've got weight acting, so weight acts down this way. Weight will be mg, and if you draw out a force diagram you'll be able to indicate these on it anyway. So you've got a certain force in the upwards direction, which you've calculated as 2 times this value that you get in here, and then you've got weight acting down the way. Subtract those two to give you the unbalanced force, and then do F equals ma. Explain why the acceleration of the capsule decreases as it rises. Well, the tension in these chords decreases. That's why the acceleration reduces. Throughout the ride, the occupants remain upright. They go into to feeling no force at all. After the release of the occupants, they feel no force between themselves and the seats. It's because both the capsule and the people in it are falling downwards at the same rate. So it's equivalent to experiencing no forces at all. So the way that you work through that question is no different from the previous two that I did. Draw a force diagram, indicate the forces on it. If you're looking at Newton's second law, always be aware of calculating the unbalanced force. The only time that calculating forces gets a wee bit more tricky is if you've got something like this. So just apply the forces at an angle, multiply it by 2 if you need to. It doesn't really change. All 3 of those questions that I've showed you, although in different situations, are asking the same stuff. So this should enable you to tackle dynamics problems a wee bit better.